with artificial intelligence, we think about machines which mimic cognitive functions that humans associate with other human minds, like, for example, learning and problem solving. There are differences in the definition. We have weak artificial intelligence, that are systems that behave like a human, but don't give us an insight into the brain. The strong AI systems, they try to mimic what our brain does. So they really want to have our brain analyzed and brought to a technology. Then we also distinguish between the AI as an entity, so for example within a single vehicle, or as a distributed organism. The keyword here is swarm technology, so having fleet technologies, swarm technologies, ant technologies, where the focus is learning of several entities and bringing this into a bigger context. Another slide about what is artificial intelligence. So in the 1990s roundabout, there were the big outcomes of machine learning things. We concentrated on statistical learning, like in Markov models, which ended especially the speech recognition, the speech understanding, and the machine translation parts. Also the natural language processing. And well, we soon came to our borders as, you converge to a certain 90% something, but not furthermore. So the investigation went towards neural networks, which at that time was a quite costly thing. So a training for a speech system with neural networks lasted 1 month or so, and was not that efficient like with HMMs. So here we had some kind of hybrid approaches, doing the pre-processing with neural networks and doing the real job with the HMMs. And this was continuing developing also with the technology, with the hardware we have, which is very efficient right now. It's very easy now to also train neural networks. And also the neural networks developed further. So starting with neural networks like recurrent neural networks, like long short-term memory networks, we continued having a deep learning approach with convolutional neural networks. And with that, we really stepped into very good object recognition, computer vision, and pattern recognition. For speech, it's also very challenging and very stable now. So also in this part, the deep learning with neural networks was pushed and was brought us very far. The other part is symbolic learning, where we use that in image processing or in robotics. So the robotics takes some different approaches. I will come to that into my talk a little bit later. And yeah, so both symbolic and machine learning give us challenges and would help us to improve for automated driving. Why? Because especially for automated driving, we need to classify the objects, the situations, we need to plan our path, and we need to predict future situations which the car comes in. For a neural network training, we could use different approaches. So we could do it with a supervised learning, which means that we know already what we want to learn and give the system human clustered training material. Or we could also tell the system, well, do it yourself. Try to find out what would be best to learn. And this is called unsupervised learning. Of course, we need to make sure that with that we really learn the solution for our problem and not a solution for another problem. And another step further would be reinforcement learning, which is taken from the bioinformatics, psychologists, informatics, which also reinforces what was learned. Like, for example, ants or bees simulating their way to the best flower whatsoever. So what does it mean for automated driving? As said, we would like to cluster and to better recognize different things. We would like to improve several ranges we have, and what you can see with the picture on with the pictures on the right, there are different road signs. So for the motorway in Germany, we have the blue sign. Italy, Switzerland, and I think also here in Serbia, it's green. And so how to train the system? What would happen if we crossed the border with an automated driving system? Would we recognize the motorway or not, if we haven't seen it before? Another thing is when we have a traffic sign, for example, which is hidden, or like in that picture, not recognizable because it's full of snow. And a third use case could be objects that come into our range, which we need to immediately recognize and do a reaction very fast. So dealing with a situation which we didn't know before. For that, artificial intelligence could give us a lot of help, which means that we could fast generate problem solving approaches. As said, some years ago it was not that fast. We needed some months or 1 month, something like that, at least some weeks for the training. But now the training is much faster than we could do by manual programming. We could also learn situations, use cases, which we couldn't foresee when doing it manually. We could also provide new solutions to known problems and then with that improve on the solution part. We could do that by unsupervised learning, always taking into account that the difficulty is to really solve the right problem and not another problem. Usually with automated driving, you fast enter very complex problem situations, and you need to solve them also mostly in a complex way. And also here, artificial intelligence gives us very good methods to solve it. And most important is that with artificial intelligence mimicking the human reactions, we would like to also have the vehicle acting more humanoid and react more smoothly. When it brakes, it's not a hard brake, but it's really looking ahead, and there's a situation where I need to brake, and you get a smooth brake and not like this hard brake. But of course, we have a lot of challenges at the moment with artificial intelligence, since usually we have a black box system which we may not understand into the very deep details, and this we would need for functional safety. Functional safety needs to make the hardware or the software safe according to the specification, And that's where the problem enters with artificial intelligence. What is the specification of an unsupervised learned system? So we will need to have a very close look on how to dealing with functional safety issues, especially if we think of self-learning situations. So not having trained a system and then it's released and comes into the car and there's no self-updating mechanism behind that. For this, we may be able to do a functional safe system quite easily, but once we want the system to self-learn during driving, during already being on the road, it's very difficult to make sure that all the functions in the car are still functionally safe. The second part, if we talk about functional safety, the next, of course, is always security. Usually with artificial intelligent systems, you exit the vehicle and enter somehow the world. So usually you want to have distributed systems, which means you have to share what you have in the car with other cars, so car to car or also car to infrastructure, car to cloud things. That means that there is a transmission to the outside world and we have to secure that. And not knowing what is inside the system, we may also get into troubles to really prevent attacks or unauthorized access. When we talk about safety, security, the next is safety of the intended function, which means not the functional safety of the system itself, but the insufficient performance of sensors or algorithms or actuators in a special situation. So the combination of what it should do and the hardware and software versus just the hardware and software and the real functionality. Also here, we first have to analyze the intended function and then not knowing what our AI system may do or not do. Next step is the user safety. So dealing with the system, humans tend to intuitively trying out things, and this may cause in a difficult situation some problems because we are somehow misusing the system, or the system doesn't understand what the human wants to have. And in that situation, especially when we are still in the level 3, level 2, level 3, level 4 situation, it may cause difficulties. What happens if we are in a situation of an upcoming accident? So the system is not able anymore to avoid the accident, but has to decide upon the situation, driving against a tree or a building, driving across an animal, or hitting a group of people. So what would the system decide to? When we have a programmed system, the responsibility, even if we are in level 4, level 5, is still with the human, because the human decided what rule should be applied to solve such a situation. With an unsupervised learned system, what is the decision here? I already mentioned about the right problem to identify. So do we really have the solution for the right problem, or did we train on something, on another problem, on something which just came with that? For example, if you train on a certain traffic sign, for example, in a morning situation. So you have morning light on that, you have the traffic sign, you train it, and then you train another traffic sign with afternoon light. So does your system really recognize the traffic sign or the light situation? And last but not least, the black box validation is very difficult, and it's very prone to maybe also have a false validation on that. But let's come to what we do at Elektrobit with artificial intelligence systems. So in the following, I would like to present you two approaches. One is taken from the neural network parts. The other one is taken from robotics. And now it gets a bit more funny because I also have some videos for you. So first of all, where is it possible to use artificial intelligence in such an automated driving approach? The automated driving approach usually has 3 columns, which is sense, plan, and act. So taking information from all the sensors we have, working on the sensor fusion, on summarizing and preparing the outcome of what we learned from the sensors, giving it to the planning part, so what means that for the ideal path, what means that for the behavior we, as the system, need to behave like, and then giving it to the actors so that it really brakes or it really drives. So the first two we concentrated on because that's where we have the chance to also have redundant systems in it, so not running into the functional safety issue with the artificial intelligence in the acting part. It's a little bit tricky, so for that we said, okay, we would like to first learn how a system can really drive within a simulation, so we would not harm anyone. What you see in the background is our EB-Robinos framework. Short on that, EB-Robinos framework is designed to have standardized interfaces between the components and the sensors, between the different components inside, and between the components and the actors. So EB-Robinos framework deals with the interfaces, and software companies, hardware companies, so sensor providers, car makers and so on, they can care about the components, about the sensors, and don't need to focus on spending too much time on the interfaces when using EB-Robinos. Okay, so coming back to the artificial intelligence. So we, first step we did was using EB-Robinos in the grid fusion part and using neural networks also in here, so having the sensors from outside and learning from them. For that we created a deep grid net. This is a neural network for grid data processing, which mainly is a convolutional network, so a deep neural network. And the input here are LiDAR data acquired from different driving scenarios, and the output should be the driving context information, so that we could distinguish between driving in a parking garage situation, driving in a city, or driving on a motorway. Okay, what do we take into account? So we take into account the environment model, which means we get information about the vehicle dynamics and the position of the vehicle. We get information about the objects around the vehicles, convoy tracks, in general, how the occupancy of the grid is given, whether we have free space in there. We get information about the road, so the road model, the linked rule sets with the road model, and also the road furniture. So if it's a new motorway and or if it's just a street on a field. And with that we could do a process of parking, city traffic and highway traffic. For a driving scene, we also use deep convolutional neural networks. And the idea here is to train on different objects, on different dynamic objects. In the first case, pedestrians crossing the street. So finding also out the direction of their movement, knowing whether it's moving or the person is moving or not. Then the second, with vehicles. With vehicles, it's a bit easier because it's more predictive, as we have also the information from the street, so we know in which direction the vehicle usually is going. And we could use that also in simulation context. And with the simulation, we prepare ourselves for the real streets. From your side, on the left, you see the ideal motorway with an ideal lightning over there, and what you can see is the lane detection in green, which goes quite far, which is quite stable, which is really promising. So this was trained with deep CNN network. But once it comes to a difficult light situation, like you see on the right side, where you have a lot of shadow, where you have objects entering, where you have light which is detected as object, it gets quite difficult to really have the full lane detection available, having it plausible and confident on that. So also the range of the lane detected is not that far as we have it with the ideal scenario. So that's where we decided to enter some other approach. We lent this the SLAM approach from the robotics. So the SLAM is simultaneous localization and mapping approach, which means that we build up, while driving, building up our own occupancy grid and closing the loop, and with every circle we get better and better, which is shown on the video on the right. And this already applies for a single vehicle. But what happens if we merge several vehicle information on that? That's where we decided, okay, why not trying to take the local environment models and bring it to some kind of global environment model, just by transferring the local environment models to a cloud system, merge it there, plausibilize it there, improve it there, and send it back to the car. What happens with that? We are able now to look around the corner and see what's behind the building. So we could already prepare on a situation behind an obstacle which we couldn't before. How does this work? Again, IB Robinos, of course. So we are still in the first sense column, which means we also take sensors from outside, doing a grid fusion, but learning from what we really get in the real drive scenario. So having the driven trajectories of several vehicles, having the actual perception of the velocity, so it's nice that the speed limit is 45 miles per hour, but why are they all driving just 5 miles per hour? What's happening there? Maybe there's some construction work where they can't drive further. There's a traffic jam whatsoever. So having this information, we could prepare other following vehicles on that situation and having them reacting properly. Having the possibility to merge and improve the situation and the data in the cloud also gives us the possibility to improve on our own algorithms, because we could then also have a look at the data, trying to find out what is the crucial thing about something. And with that, we could also create some kind of sensor map. And the system we released last year, and we implemented this also in our CES booth, but not using real cars, unfortunately, because we didn't have that big booth, but bringing it to model cars. And I'd like to just give you the video on that. Okay, we would have loved to have this, of course, in the real driving scenario, but as said, the booth was too expensive for real cars there. Okay, so to summarize, what is our vision of a cognitive approach to the future driving organism? From our point of view, we think we should have both cognitive systems based on deep neural networks and robotic-landed algorithms like the SLAM algorithm and cloud basics. Bring that to open services and give it this information to all vehicles and infrastructure and whoever participates in the traffic. And but also bringing the information, new information back from the contributors and improve the system. And I don't know who already saw the parking demo outside. We also had one.
Remotely control the parking process of your vehicle by starting the parking app on your mobile device. The vehicle receives information by the intelligent parking infrastructure about the most suitable free parking spot, as well as the exact path to take there. The vehicle sensors determine its position. The respective location is then transmitted to the server. The server plans the path to the parking spot and sends the information to the vehicle that heads out to it. While the vehicle is moving, the parking garage monitors obstacles and adapts the path. The vehicle is only double-checking its way. LiDAR sensors are deployed throughout the parking garage to monitor spaces and perceive static as well as dynamic obstacles. A static map defines lanes and forbidden areas. The positioning of the vehicle is automatically corrected. The vehicle can control all actuators on its own while proceeding to the parking spot. A driver is not required. The vehicle reaches its destination and parks itself in the parking spot that has been assigned by the server. Through his app, the driver is notified that his vehicle is parked successfully. Our approach provides a more convenient parking process for next-generation parking garages, allows for an optimized traffic flow, and enables additional services like autonomous e-charging.
But yeah, this was our approach at the IAA. The parking garage was a normal parking garage, so there were other cars driving around as well. There were pedestrians crossing and so on. And we had this demo together with our mother company, Continental, who did a similar demo, but just on in-car sensors. And that was my talk. Thanks for your attention, and I'm happy if you have some questions for me. Thanks.